This lesson is about the use of excess and limiting reactants in chemical reactions. The first thing we want to do is define what a limiting reactant and excess reactant are. This situation can be described as having too much of one reactant and not enough of the other. It can be exemplified by this situation where we want to bake cookies and we line up our ingredients. Now, when we line up our ingredients, we can see that we have plenty of flour, eggs, and butter, but we don't have enough sugar. And if we measure our quantities, we may discover that each quantity of the ingredient will allow us to bake a different number of cookies. So the question is, how many cookies can we bake and how much of the other ingredients will we have left over? Now, the sugar in this example will be our limiting reactant because it's limiting our abilities to bake cookies. So the number of cookies that we can actually produce is the one that is given by the limiting reactant. So we can define as limiting reactant the one that is used up first, or the one that is completely consumed by the reaction. And we call excess reactant the one that is present, or the ones that are present in greater quantities than actually needed. So let's look at an example in chemistry. For our reaction of carbon monoxide with hydrogen gas, suppose we have 5 moles of carbon monoxide and 8 moles of hydrogen gas. How many moles of methanol can we produce? Now, when we look at the numbers that we're dealing with, we can see that unlike when we were working with exact quantities, we have quantities that are not exact. So what we need to determine is which one is the limiting reactant. And once we determine which one is the limiting reactant, we can use that ingredient or chemical to determine how much product we can produce. In order to analyze the quantities involved in this reaction and determine which one is the limiting reactant, we can set up and fill in a table like we did before. So we set up the table with the chemical species and we enter the coefficients. In the line of moles, we're going to enter the quantities that we are provided, 5 moles of CO and 8 moles of H2. Unlike before, where we could determine the amount of product from either one of the exact quantities provided, in this case, we notice that if we use the 5 moles of CO, we are going to obtain 5 moles of CH3OH as a product, but if we use the 8 moles of H2, divide by 2 times 1, we obtain 4 moles of CH3OH. We can explain this difference by understanding that these quantities are not exact, and one is a limiting reactant. So which one is the limiting reactant? To determine that, we can calculate how many mole of each reactant are required for the reaction with the quantities given. So 5 moles of CO, we can calculate require 10 moles of H2. However, we don't have 10 moles of H2, we only have 8, which means that H2 is our limiting reactant. Once we determine this, we can establish that the table that we need to use to determine the product is the one originated by using the 8 moles of H2, which determine that we need 4 moles for the CO for the reaction. Because we have 5 moles and only 4 are needed, CO is the excess reactant. At this point, we can easily calculate the quantity that is needed for that is going to be produced from this reaction from the 8 moles of H2, and this gives us 4 moles of CH3OH. The quantity of excess reactant left over is also easily calculated as the difference between the moles actually present, which are 5, minus the moles that are needed for the reaction, which are 4. So 5 minus 4, 1 mole of CO. We're now going to look at an example on how to do this. So I'm going to pass on to my notepad. And what we have here is the reaction between sodium bromide and phosphoric acid. Now, we looked at this reaction previously with exact quantities, and we've seen that if we have 0.327 moles of NaBr, we can calculate the moles of H3O4 needed for the reaction. Let us assume that actually we have available this quantity of NaBr and 0.2 mole of H3PO4. So let us calculate. So what we're going to do, we're going to set up our table. We're going to place our coefficients down here. And then we're going to place our initial mole, 0.327. And then we're going to calculate how many moles of H3PO4 are needed for the reaction of 0.327 moles of NaBr. Notice that I do not plug in the 0.2 moles of H3PO4 because these quantities may not be exact. So what I get is 0.327 divided by 3 multiplied by 1 gives me 0.109 mole. Now, by comparing the moles needed for the reaction with the moles available, I can see that I have more than plenty mole of H3PO4, and actually I have an excess of 0.200 minus 0.109 mole of H3PO4, which will be the amount of excess reactant left over. In general, what we deal with is we don't have moles given. So we may have moles given, but we also may have masses given. So if masses are provided instead of moles, how do we solve? So let's look at an example, which is the reaction of magnesium and oxygen to produce magnesium oxide. And let us assume that we are provided with 5 grams each of the reactants. Now, once we're provided with those amounts, we need to convert those into moles in order to determine the amount of product produced. However, we do know that these quantities may not be exact. So I'm going to pass on to my notepad to solve this problem. So I have my reaction here. So 2 moles of magnesium plus oxygen forms magnesium oxide. And I'm going to set up my table with the magnesium, the oxygen, and the magnesium oxide. And I can set it up when I have the grams, I have the mass in grams, I have the molar mass in grams per mole, then I have my moles, and I have my coefficients. Now, the molar mass can be plugged in, so 24.3, 32.0, and then 40.3. And the coefficients are filled in from the chemical equation, so 2, 1, 2. At this point, I'm going to take the 5 grams of magnesium, and I'm going to try and determine how much oxygen I need for this reaction. So 5.00 grams of magnesium divided by 24.3 gives me 0.206 moles of magnesium. Divided by 2 times 1, I'm going to get 0.103 moles of oxygen. And at this point, I can multiply by 32 to see how many grams of oxygen I need for this reaction, and will give me 3.30. Now, because I have more than 3.30, it means that the oxygen is the excess reactant. So oxygen will be the excess, and magnesium is my limiting reactant. Now, that means that I can react 5 grams of magnesium to, which will be completely consumed, to produce magnesium oxide. So from the 5 grams of magnesium, I can calculate the amount of magnesium oxide needed. So this will give me 0.206 moles of magnesium oxide multiplied by 40.3 will give me 8.30 grams of magnesium oxide produced. Amount of oxygen left over is going to be my 5.00 grams minus the 330 that I'm actually using for this reaction. And so that will give me the amount of oxygen left over in grams. Or I could calculate that in moles if I wanted to. Now, what if we had started our reaction from the excess reactant? In that case, we would have come out with a quantity of magnesium which is higher than 5 grams. So we would have a table that is not usable because we don't have enough of one of the reactants. So when we do the table, we need to use the table based on the limiting reactant.